All right, guys, so we are getting closer towards the end, so we're going to go ahead and start this Unit 10 study guide. So some things you'll need is your periodic table handy, your polyatomic ion list, and then also your activity series chart. It had basically the giant arrow on the side, basically ranking your metals for single replacement, and we'll talk about that a little bit. So it's just handy to have those next to you so you can refer to those if you need to. And then feel free to pause if you ever want to, and then you can work out these problems and see if it matches up to mine, or rewind, or just skip to any parts that you kind of need help with. Okay, so I'm going to get started on this first section first. Let me make sure I'm in the right font and everything. So we're going to talk about our 5 types of reactions. I'm not going to go in super detail on this. I know the keys are going to be a little bit more in detail, but I'm just going to touch base on the general rules and what each one is. Okay, so your first one is synthesis. So synthesis is when you actually create something from 2 different parts. So your general reaction would be something like A plus B gives me AB. Okay, so the main thing that you're looking for here is you have 2 different reactants in the beginning and you have only 1 product in the end. Okay, so I'm going to put this right here. You only have 1 product. That is a dead giveaway for synthesis. So if you only have 1 thing in the right-hand side, that is synthesis. Now your rules, so as far as your rules, if something goes like binary, like if you were to just take sodium and chlorine, okay, then it would just turn into sodium chloride. Okay, so those are pretty easy to see. The other ones you kind of got to look out for is you can go by the rules based off your chart, but when I do synthesis, I look for 2 things that I can make. If I can make hydroxide, I will. And if I can make a polyatomic, I'll make a polyatomic. What I mean by that is if I can make carbonate, so that's CO3, and then chlorate is ClO3. Okay, and we'll do examples on that here in a little bit and stuff, but this is the way I kind of remember it here once you get past that binary. Okay, decomposition is going to be the opposite of synthesis. This is where you have 1 reactant in the beginning and it breaks into pieces. Okay, that's what decomposing means, to break apart or break down. So that's the big tell right there, is if I only have 1 reactant, so I'm going to put that over here as a star. If I have 1 reactant and it breaks into pieces, that is decomposition. Okay, so again, if it's something as simple as binary, so if I had something like NaCl, what I mean by binary is just 2 different elements, that's it. Okay, so all it's going to do is just break apart. So it's going to Na plus Cl, that's it. Now when you get into actual kind of more complicated things, so you've got like an element with a polyatomic, things like that, that's when it kind of gets a little tricky, and we'll do plenty of examples, but the 3 things I look for decomposition is if I can make these in this order, I'll make them. So my first option that I want to try to make is H2O. If I can make H2O, that'll be my first option. My second option would be CO2. If I can make CO2, I'm going to make CO2. And my last option, if I can, I'm going to make O2. So again, I'm going to show you how those kind of come into play when we actually do the examples. Single replacement, so this is when you have something by itself, so like an element A is by itself, and then you have a pair, and that A is trying to make its way into that BC pair. Okay, so if A is good enough, like say A is now going to take B's place, now A will be a C, and now B's off by itself. Okay, so the way I usually tell my students is just like in real life, if you're in a couple or a pair, okay, you're not going to dump your boyfriend or girlfriend for someone worse. So it has to be something better. Okay, so A has to be better than B for C to switch partners like that. And that's what we use the activity series for. Okay, and you have to determine, is the metal better than the other one? Okay, and we're going to do more examples on that. So a lot of the rules you can kind of get from the key and just the general statements of it, but I want to talk about just kind of about what each one is, and then focus more on the examples which you actually see on the test. Okay, double replacement is when you actually have a pair, so A and B, and another pair, C and D, and this is just called a partner swap. Okay, so now A is going to go with D, and C is going to go with B. Okay, double replacement, it usually looks the most complicated because you have the most stuff. Okay, but all it is a partner swap. Okay, then you have combustion. Okay, combustion, always looks the same. You have a hydrocarbon. So usually you have a certain number of carbons and you have a certain number of hydrogens, or there can be some oxygens in there. But the key thing is it reacts with oxygen gas, and this is going to produce CO2 and H2O. So combustion always looks the same. These three right here always look the same. Okay, so that would be a dead giveaway. So combustion is mostly just balancing. That's the biggest thing. Okay, and we'll get into more examples on that. So to explain the law of conservation of mass and give 2 examples, the big thing here is, I'm just going to give you the general idea of it, is that you cannot create or destroy atoms. Okay, you can kind of through like nuclear fission and stuff like that, but that's beyond what we're talking about right now. What we care about is the mass you had in the beginning equals the mass you had in the end. Okay, or the atoms you had in the beginning of the reaction better be the atoms you have in the end. Okay, so whatever you start with better be what you have in the end. So if I had something like 5 carbons in the beginning of the reaction, I better have 5 carbons in the end of the reaction. Okay, because we can't create carbons and we can't destroy those carbons. Okay, so that's the main thing, is why we balance. So this is where that balancing comes into play, is we have to make sure we have a conservation of mass. Okay, number 3, identify each reaction as synthesis, decomposition, single replacement, double replacement, or combustion. Correctly balance each equation and then list the order of the coefficients. Okay, first, the order of coefficients is just simply this number, these numbers right here. If you don't see anything right there, like in front of this O2, that's just like an imaginary 1. So that's where you see this 1 come from right here. Okay, so we're going to look at number 1. I have 2 reactants. I have iron and oxygen, and I make iron oxide. So I only have 1 product. So this is going to be a synthesis. Okay, so now what we're going to do is a balance. Okay, so some of these you can just kind of look at. Okay, so I've got 1 Fe on the left side. I've got 2 Fe's on the right side. I can go ahead and put a 2 here to see if I can balance out those Fe's and see if that helps. So my irons are balanced. And I have 2 oxygens on the left, and I have 3 oxygens on the right. Well, 2 can't go into 3, and 3 can't go into 2. So therefore, I need to find the closest number that can be divided by both 3 and 2. Okay, so the closest number would be 6. So I need to get each one of those oxygens to 6. So I'm going to multiply this O2 by 3. And this Fe2O3 by 2. Okay, so now I have 6 oxygens on the left and 6 oxygens on the right. But, so this fixed my oxygens, but this also multiplies my iron. So now I have 4 irons on the right and only 2 on the left. So what I'm going to do is I'm just going to cross this 2 out and put a 4. And then there we go. Now we're nice and balanced. So this would just be a 4, 3, 2. Okay. Aluminum plus iron oxide gives me aluminum oxide and iron. Okay, so I have a single element right here. Okay, and it replaced that iron, and now iron's off by itself. So this is the single replacement. Okay, so I'm going to see how many I got. I've got 1 aluminum on the left, 2 aluminums on the right. Okay, so I can go ahead and put a 2 here if I want. Okay, I've got 1 iron on the left, 1 iron on the right, so that one's good. I've got 1 oxygen on the right, I'm going to say on the left, and 3 oxygens on the right. So I'm going to do is I'm going to put a 3 right here, okay, to fix those oxygens. Okay, but this also multiplied my iron by 3, so that means I had to put a 3 over here. Okay, so I didn't have to do anything to this aluminum oxide, so that's imaginary 1 right there. So this would be a 2, 3, 1, 3. Okay, next one I have aluminum hydroxide, and then this looks like sulfuric acid, H2SO4, gives me Al2SO4 plus H2O. So I have a pair, and it looks like I have a pair and a pair in the end. Okay, so this is going to be a double replacement. So double replacements usually look the most complicated because it's got the most stuff. Okay, so as far as balancing goes, so here's a little trick that I do. Okay, so if it gets complicated like this, you can write out the elements that I'm trying to balance. Okay. If I have a hydroxide right here, and I have a hydrogen off on its own right there, Here's a little trick that I do sometimes is I will change this H2O to HOH. So now I treat it as one hydrogen by itself and a hydroxide by itself. Okay, so I'm going to do aluminums, hydroxides, I'm going to do hydrogens that are by themselves, and I'm going to do SO4. So if I have sulfate on this side and I have sulfate on this side, it is a lot easier to keep those together as sulfate than if you were to try to split that up as S's and oxygens. Okay, if you try to break all this up individually, it's going to be a long time. So I have one aluminum on the left. So again, this 3 right here does not affect that aluminum. It affects my hydroxides. I have 3 hydroxides. I've got 2 hydrogens on the left, and I've got 1 sulfate. Okay, on the right, I got 2 aluminums. I got 3 sulfates. I have 1 hydrogen by itself, and I have 1 hydroxide. Okay, so I'm going to start off with aluminums. I have 1 aluminum on the left, so I need to get to 2 to match. So I'm going to put a 2 right here. So now this changes my aluminums to 2, but it also changes my hydroxides to 6. Now 2 times 3 gives me 6. Okay, so make sure you update this as you go. Okay, so I'm going to move on to my hydroxides. I need 6 on the right, so I'm going to put a 6 right here. Okay, so this changed my hydroxides to 6, but it also changed my hydrogens to 6. Okay, so I'm going to need to fix my hydrogens now. I'm going to put a 3 in front of this H2SO4. Okay, and so that's going to multiply my hydrogen to 6. And now I have 3 sulfates, so that was 2 birds, 1 stone. So this is nice and balanced. So this would be a 2, 3, 1, 6. Okay, P4 plus O2 gives me P2O5. Okay, so I have a reactant and a reactant. I make one thing. This is called synthesis. Okay, so I'm going to do this. So I'm going to try this route again. So I have P and I have O. I've got 4 P's on the left, 2 O's on the left, and I've got 2 P's on the right, and 5 O's on the right. Okay, so I'm going to fix my P's first. So I usually try to save oxygen for last. That just makes things a lot easier if you save oxygen for last. So I'm going to multiply this by 2 to fix my P's. So this is going to go to 4. But now my oxygens are going to go to 10. So I need to get to 10 on the left. So I'm going to multiply this by 5. And now I have 10. So now this means I'm good. So this would be a 1, 5, 2. Okay, here I see this big long chain right here, and I have O2, CO2, and H2O. This is a dead giveaway that this is combustion. Oops. Fix that. So this is combustion. Okay, so combustion is just a matter of balancing. So what I'm going to do it over here. So I have CHO. So I do this the exact same way every single time. So I'm going to count how many carbons I have on the left. I have only 2 carbons on the left. I have 6 hydrogens on the left. Okay, and I have 3 oxygens. On the right, I have 1, 2, 3. So I'm going to start on my right side. I'm going to multiply this by 2 to fix my carbons. Okay, but this changed my oxygens now. So 2 times 2 is 4, plus, don't forget this one right here. Okay, so this is 4 plus 1 gives me 5 oxygens. So I'm going to move on to my hydrogens. I need to get to 6, so I'm going to multiply this by 3. This changes this to 6, but it's affected my oxygens again. 2 times 2 is 4, plus 3 times 1, I now have 7. Okay, so I need to get to 7 on the left. The last thing you want to do is put anything right here. Okay, because if you do, you're going to start all over again. So I need to see if I can manipulate this. So I need to get to 7 oxygens, but I'm not going to forget about this oxygen right here. So I need to know 1 plus what gives me 7. Well, that's 6. So that means all I got to do is multiply this by 3, and now I have 7 oxygens. So my answer would be a 1, 3, 2, 3. Okay, so moving on to the next one, I have, looks like only 1 reactant, and then it breaks apart. So this is going to be a decomposition. Okay, so I'm going to do this the same way. So I'm going to do hydrogen, I'm going to do arsenic, and I'm going to do oxygen. So I have 3 hydrogens on the left, I have 1 arsenic on the left, and I have 4 oxygens on the left. I have 2 arsenics on the right, and I have 6 oxygens on the right, and then I have 2 hydrogens. Okay, so I'm going to start with hydrogen. I've got 3 hydrogens on the left, 2 on the right, so the closest number that can be divided by both is going to be 6. So I'm going to see if this works. I'm going to put a 2 right here. So this is going to change this to 6, changes my arsenics to 2, and it changes my oxygens to 8. Okay, but I cannot forget that I need to fix my hydrogens over here. I'm going to put a 3 right here. This changes my hydrogens to 6, but it also changed my oxygens. 5 plus 3 is now 8. Okay, so this actually balanced out real easily. So this is a 2, 1, 3. Okay, F2NaCl gives me Cl2 plus NaF. I have something by itself, so even though there's an F2 right here, that's still considered a single. Okay, and there's a Cl2 right here, that's still considered a single element. Okay, that does not count as a pair. So this is going to be a single replacement. Okay, so I've got 2 F's on the left, only 1 on the right. So I'm going to put a 2 right here to fix that F. But that also changes my NAs to 2 now. So that means I have to fix my NAs on the left. So I'm going to put a 2 right here. So that fixes my NAs. And now that changed my chlorines to 2 on the left. And now I have 2 chlorines on the right. So that means this one's done. So this would just be a 1, 2, 1, 2. Okay, back to this one. I see O2, CO2, and H2O. This is going to be a combustion. Okay, so I'm going to do my same trick. So I usually do this every time for combustion because sometimes you can run into a little problem. Okay, so I have 7 carbons on the left, 6 hydrogens on the left, and I have 4 oxygens on the left. And on the right, I have 1, 2, 3. I'm going to start with carbons. I need 7 on the right, so I'm going to put a 7 right here. That changes this to 7. Also, if it changes my oxygen, 7 times 2 is 14, plus this 1 gives me 15. Okay, I'm going to move on to hydrogens. I need 6 on the right, so I'm going to put a 3 right here. This changes this. Also change your oxygens again, so just recount your oxygens completely again. I have 7 times 2 is 14, 3 times 1 is 3, so 14 plus 3 gives me 17. Okay, so again, we said last thing we want to do is touch anything right here, because then we start all over. So I need to know what can I put right here. So this 2 is stuck. So 2 plus what gives me 17? Okay, that means this right here would have to be a 15. So what I'm going to do is, here's my trick, the way I do it. So I'm going to take this 15 divided by 2. That gives me 7.5. So I'm going to put 7.5 right here. So here's the thing, is you can't have 7.5 atoms. So what I'm going to do is I'm going to double this and make it 15. Okay, so I don't want that 0.5, so I doubled it. But if you do this trick, you double everything though. This imaginary 1 right here becomes a 2. This 7 becomes a 14. And this 3 becomes a 6. Okay, so this makes everything balanced. Okay, so I'm not going to go through and count all those and stuff, but if you don't believe me, just pause it and check it and stuff. But there's that little trick. If you get stuck, just do the decimal and then double everything. So this would be a 2, 15, 14, and 6. Okay, these next ones, I'm going to kind of just do, I'm going to just talk about what they are because we're going to do more balancing here in a bit. So here I have a reactant and then it breaks down into 2 products. So this would be decomposition. And then this last one here, I have a pair, and I get a pair and a pair. So this is a double replacement. Okay, so you can check the key for these 2 right here. But I want to try to kind of move on a little bit. So we're going to go into describe the evidences of a chemical reaction. Okay, so the main thing here is when you see a chemical reaction, 1, there can be a color change. Okay, so that means when you have substances that would produce a color that you would not expect, okay, that would be a color change. So like blue and yellow would make green. Okay, but if I took blue and yellow and I got red, okay, so that's going to be an example of a chemical reaction. Okay, so it has to be a color that you weren't really predicting. 2 would be a temperature change. So if I had something that produced heat or basically lost heat, okay, you got colder, that would be a chemical change. Sorry. 3, when I start seeing bubbles, okay, or a gas is produced, that is another method or another determining factor of a chemical reaction. Okay, I have 4 precipitate forms. Precipitate just means a solid. So basically what happens is if I took 2 liquids or 2 aqueous solutions and I made a solid from those, that would be a chemical reaction. Okay, number 5 would be if water was produced. Okay, so that means usually that comes from your acid-base reactions. I take an acid and a base, neutralize them, that produces water. Okay, and then my last one is going to basically be light is emitted. It creates a light, like a flash, okay, or it actually absorbs light. Okay, so you don't have to worry about too much about those. Okay, so but just kind of, you do need to know these. We don't have to go too in depth on these. Okay, these are just evidences of a chemical reaction. Okay, number 5, list the 7 diatomic elements. The way I remember this is the name Brinkelhoff. So Brinkelhoff, B-R-I-N-C-L-H-O-N-F. Okay, so those are your 7 diatomic elements. So di means 2, meaning these do not like to be by themselves. Okay, if they're bonded with somebody, they don't have to have 2. But if you ever see bromine off by itself in a reaction, it's always Br2. If you ever see hydrogen off by itself in a reaction, it's H2. Okay, but when you take hydrogen and bond it with something else, don't think you have to always have 2. It's only when they're alone. Okay, so they have to be in pairs. Okay, so let's move on to this one. Okay, so we talk a little bit about in class the main driving forces for double replacement. First one is precipitate formation. This basically just when you form a solid. Okay, so that's a kind of a driving force. Usually you're going to see those like in your double replacement reactions, because that's when something doesn't fall in the Cashingia. Next one is gas formation. All we're doing is we're just producing gas. Okay, so this can happen in double replacement. It can happen in double replacement. It can happen in decomposition. Remember, decomposition, I can make O2 or CO2 gas, or combustion. Okay, combustion always makes CO2. Water formation, this is just producing water. So nothing fancy here. Okay, but these are just your 3 driving forces. So combustion always makes water and CO2, and then we usually get water from our acid-base neutralization. So those are kind of just your 3 driving forces. Not a whole lot in there, so I wouldn't worry too much about that. Not going to go too far in depth on that. 7, write S for precipitate, forms a solid, or AQ for aqueous, remains in solution. So this is your Cashingia. So we're going to touch base on this. So Cashingia, so C-A-S-H-A-N and Gia. Okay, so this was something you really need to know this. Okay, so C, most of these you can find on your polyatomic list. C stands for chlorate. Okay, that is not carbonate. That's a big difference. A stands for acetate. That one's on your polyatomic list. Chlorate's on your polyatomic list. S stands for sulfate. That's on your polyatomic list. H is your halides. That's on your periodic table. I think of this, I remember the name Brickle. So bromine, iodine, and chlorine. My other A is ammonium. That's on your polyatomic list. And then the last one in N is nitrate. That's on your polyatomic list. And Gia means group 1A. That just means the first column on your periodic table. Okay, so starting at hydrogen, kind of going down. Okay, so remember, if you're on this list, you have at least one of these on that list, it means you're aqueous. Okay, if neither of you on that list, that means you're solid. But you do have to watch out for these bad guys right here. Your 3 bad guys are silver, which is Ag, lead, which is Pb, and then mercury, which is Hg. Okay, these are only bad, meaning they make it a solid if it's attached to these 2 right here. So you can have those attached to the other ones and it's still aqueous, but not when it's attached to those 2. Okay, so the phrase we use is bad guys need to shh. So that's one way you can remember it. So we're just going to go through here and see if these are on that list. So sodium is in group 1, Chlorine is a halide, so this is both of them on that list, so this would definitely be aqueous. Calcium is in group 2, so that's not on there, but sulfate is on there, so this is aqueous. Okay, sorry, my cues look bad. Okay, zinc is not on my list. Chlorine is, though. It's a halide, so this is aqueous. Chromium is not on my list, but nitrate is, and chromium's not a bad guy or anything like that, so this is aqueous. Hydrogen is on my list. Sulfate's on my list, so this is aqueous as well, so we're bound to find one here in a second. Ag, so watch out, this is a bad guy, and it's attached to a chloride, so that means chlorine, which is a halide, so that means this is now a solid. Magnesium is in group 2, so that's not on my list, and carbonate's not on my list either, so this is solid. KOH, potassium is in group 1, hydroxide not on my list, but since potassium's there, this is going to be aqueous. Iron sulfide, so Fe is not on my list, and sulfur is not on my list. Sulfate is, but that doesn't mean sulfur. Okay, so this is going to be a solid. Li, so lithium is on my list. Phosphate is not on my list, but as long as I got one, AQ. Both hydrogen and nitrate are on my list, so this is AQ. HgCl2, so watch out for that mercury. It's attached to a halide, so now this is a solid. Sr is strontium, and then hydroxide. Okay, so strontium, that's on my list, on the group 1, and then OH. Okay, so usually this one can kind of go either way. I'm not going to really do this. This one can be aqueous, okay, because it's a base in this situation. Okay, but we're not going to try to give you anything that's kind of that confusing on there. And then NH4 so that's ammonium, and that's a salt. So ammonium's on my list, so this is aqueous. Copper's not on my list. Phosphate's not on my list. Okay, so this is going to be a solid. Aluminum's not on my list, but chlorine is, and aluminum's not a bad guy, so this is aqueous. Okay, sodium is on my list. This is aqueous. Cobalt is not. Carbonate is not, so this is solid. Okay, francium is on my list. That's in group 1A. Okay, so this is aqueous. And then ammonium's on my list, so that is aqueous. Okay, so you really got to know that Cash and Gia. Number 8, describe the acid-base neutralization reaction and give an example. Okay, basically what you need to know is when you take an acid plus a base, you're going to get H2O, you're going to create a water and a salt. Okay, so I'm just going to think of one for a second. So what if I do like H2SO4, that's sulfuric acid, and then let's say I do sodium hydroxide. Okay, there's my base. Anything that ends in hydroxide is a base. Okay, so remember acids, anything, we're going to go with these in just a second. Acids always start with hydrogen, and bases always end with a hydroxide. So when I take an acid and a base, I'm going to take this it's basically a partner swap. I'm going to take hydrogen and a hydroxide and put them together to make H2O. And then I'm going to take this sodium and this sulfate, and I'm going to make a salt. Okay, so this becomes a sodium sulfate, so this is going to be Na2SO4. Okay, so that's kind of the gist of acid-base neutralizations. Number 9, identify each of the following as ionic, covalent, or an acid. Then write the name. Okay, so this is a big thing, is just knowing the names and how to write the formula. Okay, not so much the ionic versus covalent. I mean, that does help with the naming and stuff, but a lot of students have issues with just getting usually the formula from the name. Okay, so that's why we're going to do this. So ionic, remember that's when you take a metal and a non-metal, so something from the left side of the periodic table of that staircase and then something on the right side. Covalent is when you take a non-metal and a non-metal, so both on the right side of that staircase. And then an acid always just start with a hydrogen. Okay. Okay, before we get into the kind of this naming, I'm going to also refresh you a little bit. There's 2 types of acids. You have binary, and then you have ternary. Okay, binary just means 2. Okay, so binary would be something like this, like the first one, HCl. I have just two elements. Binary always uses hydro. Okay, so hydro, you can think of no O. So that means no oxygen. Hydro, no O. Okay, so that's basically it. And then acids are always usually end with ic. Okay, so this one's always going to end with ic and the term acid. Ternary. Okay, ternary is when you actually start dealing with polyatomics now. So polyatomic, so this means, one, there's no hydro. We do not use hydro for ternary. Okay, so the example of this one would be like HClO3. Okay, that is a polyatomic ion. That is chlorate right there. So we don't use hydro. So that's one thing you need to look for is the term hydro. That can tell you what it is. Now, if the polyatomic ends in ate, your acid will end in ic. If your polyatomic ends in ite, it will now end in us. Okay, so there's kind of your refresher. So we're going to get into this. I see HCl. So this is binary. So that means I'm going to use the term hydro. And now chlorine just becomes chloric. So this is hydrochloric acid. B, lead 2 sulfate. So lead 2, this tells me the charge of lead. So if you need to do this, you can write up top. Pb with a +2. Sulfate is SO4 with a -2. So if these numbers match, just put them together. So this would just be PbSO4. N2O4, so nitrogen and oxygen, they're both on the right side. So this is going to be a covalent. Oh, so let me label these. This is an acid. This is ionic. Okay, this is going to be covalent, meaning they're both on the right side. So covalent means we use prefixes. So 2 is di. So this is going to be dinitrogen. 4 is tetra. So this is going to be tetraoxide. So if you need a refresher real quick, mono is 1, di, that's 2, tri, tetra, penta, that's 5, and then you have hexa, 6, hepta, 7, octa, 8, nona, 9, and deca is 10. Okay, so this is dinitrogen tetraoxide. MgOH2, so we know this is a base, but it's not asking for a base because if it's ending in hydroxide, that makes it a base. But this is going to be considered ionic because magnesium is a metal. Okay, so ionics are easy, just name them out. So Mg is magnesium, and then OH is just hydroxide. So nothing fancy there. Sulfuric acid, so here's the key thing. 1, I don't see hydro. Okay, 1, this is an acid. I don't see hydro, so this means this is ternary, meaning I'm dealing with a polyatomic. Okay, it ends in ic, and we know hydrogen always starts with an H. If it ends in ic, that means we're doing a sulfate. This is SO4 with a -2. So that means it's not balanced. So I'd take that 2 from the SO4 over to the hydrogen, and the 1 from the hydrogen to the SO4. So that means I need 2 hydrogens to balance out with that SO4. HNO2 starts with an H, so I know this is an acid. So I'm going to look here. So 1, I see a polyatomic, so this is going to be ternary. Okay, and then NO2, that's nitrite. So remember, if it ends in ite, it ends in us. So this is nitrous acid. So you notice that I did not use the term hydro. I only use hydro on binaries. That's just 2 elements. That's it. Okay. 6, PCl. Okay, so PCl3. So if you look on your periodic table, phosphorus is on the right side of that periodic table. So is chlorine. Okay, so this is going to be covalent. So we never use mono on the first one. So this is just going to be phosphorus. And then 3 is tri, so this is trichloride. Okay, carbon tetrabromide. So as soon as you see the term tetra, that means instantly it's a prefix, which means it's covalent. So this would just be C, 1 carbon, and 4 bromine. So Br4. Aluminum phosphite, I have a metal and a non-metal, so this is going to be ionic. So aluminum is Al with a charge of +3. Phosphite is on your polyatomic list. That's PO3 with a -3. My numbers already match, so all I got to do is put them together. So this will just be Al, PO3. Phosphorus acid. Okay, so I know acids always start with an H, and this is an acid. Sorry. And then phosphorus acid, that means I'm dealing with phosphite. Okay, so this is PO3 with a -3. So these aren't balanced, so I'm going to do the crisscross, so that means I need 3 hydrogens and only 1 phosphite. Okay. Next one, hydrofluoric acid. So this is an acid. There's your term hydro. Hydro means this is just polyatomic. So binary. This is just, we have hydrogen, we know that. And that means we just have fluorine, that's it. And fluorine has a charge of -1. So this would just be HF. ZnCl2, zinc is a metal. So this is going to be ionic. Okay, zinc always has a charge of +2. That's one of the exceptions on your transition metals, so you do not need a Roman numeral. So this is just going to be simply zinc chloride. M, iron, so I have Fe2, so Fe is iron, and then oxide. Now, iron is a transition metal, so if I have a metal and non-metal, this makes it ionic. Transition metals need a Roman numeral, so it's based off the anion. Okay, so if it's bonded with 3 oxygens, you can also do the reverse crisscross. Take this 3 up here, take this 2 up here. If that 2 matches the charge of oxygen, it works. So oxygen has a charge of -2, so that's correct. So that means this iron has a charge of 3. So you're going to put iron 3 oxide. HClO3, so starts off with a hydrogen, so we know this is an acid. I'm dealing with a polyatomic, so that means we're dealing with a ternary acid, so we don't use hydro. ClO3 is chlorate. Remember, if it ends in 8, it ends in ic. So this is going to be chloric acid. Okay, last one, acetic acid. So we know it's an acid. It starts with a hydrogen. Acetic is just acetate, which is C2H3O2 with a -1. Okay, already balanced, so this would just be HC2H3O2. Okay, so if you need to go back and look at this again or practice some more, this is probably the number one mistakes we see is just from simply getting the correct formula from the name. Okay, 10, now we're going to go into skeletal equations. Okay, we're going to write the following reactions, include states of matter, and do not balance the reactions. We're not going to balance yet. Okay, so I'm going to go through some key terms to look for. So A, aluminum metal. So metal means a solid. Okay, so we're going to start off. Aluminum is off by itself, and aluminum has a charge of +3. I'm going to write that up here just in case I need it later. So Al, and that's a solid, reacts with, okay, so there's going to be a plus, aqueous, there's our state of matter, zinc chloride. So this is where I write things out individually first. So zinc has a charge of +2, chlorine has a charge of -1, so these are not balanced, so you need a crisscross. So my correct formula for that would be ZnCl2, and that was aqueous. Okay, produce, so that means I'm going to draw my arrow. Zinc metal. So now zinc is off by itself, so it looks like this was a single replacement. And metal means a solid. And aqueous, aluminum chloride. So remember, aluminum has a charge of +3. Chlorine has a charge of -1. These are not balanced, so you're going to do crisscross. So that means I need 3 chlorines to balance out that 1 aluminum. So this is AlCl3. Okay, and this was aqueous, it told me, and that's it. So that means we don't have to write the numbers in front. We're not trying to balance here. But you always have to balance based on charges. If you're going to put something with something, you better balance based on charges. That's the same every single time. B, when mixed, solutions. So if you see the term solutions, this means aqueous. Of lead to nitrate, so that means lead has a charge of +2. Nitrate is NO3 with a -1. and calcium chloride. So calcium is Ca with a +2 and chlorine with a -1. Okay, so that means I'm going to put, these are my two reactants, so I'm going to put them together. So Pb +2 NO3 -1, not balanced, so it means you crisscross. So that means I need 1 lead and 2 nitrates. I'm going to put that nitrate in parentheses and then put a 2. And this was aqueous because it told me. Calcium chloride, so +2 -1. This is not balanced, so this would be CaCl2. And this is aqueous as well. And I'm going to reform, so I drew my arrow. Lead 2 chloride, so this is Pb with a +2, chlorine with a -1. So this is not balanced, so this would be PbCl2 plus calcium nitrate, so calcium has a charge of +2, nitrate has a -1. So this would be CaNO3 2. So now I'm going to see what states of matter they actually are because it didn't actually tell us. So I'm going to go off my Cash and Gia since it's a double replacement. So I have lead, which is a bad guy, and it's attached to a halide. So that means this is actually a solid now. So halide is normally on my Cash and Gia list, but that lead is a bad guy. Calcium's not on my list, but nitrate is, so this is going to be aqueous. And that's it. Okay, solid carbon disulfide. So this would just be 1 carbon disulfide, so CS2. Reacts with oxygen gas. So remember, oxygen is part of that Brinkelhoff, so you can't just put O. This has to be O2. And that's a gas. Okay, and then it said solid for my carbon disulfide, so I'm going to put that in S. To produce carbon dioxide gas, that's CO2. I'm going to put a little G. And sulfur dioxide gas. So this is sulfur and 2 oxygens, and that's a gas. Okay. So now we're kind of getting into the meat of this. So we're getting to this. So I'm going to take a little time on this, but I'm trying to go through this as quick as I can. Okay, but this is now kind of the meat and potatoes. What we're getting to is it kind of adds it all up. So we're going to predict the products now, identify the type of reaction, and then we also balance it. So this is kind of everything. Okay, so we're going to start off number 1. This is the way I do it every single time. Hydrochloric acid. So hydro, meaning this is just 2 elements, meaning H+, and chlorine, which is Cl-. Reacts with magnesium metal, so this is going to be magnesium with a +2, and it's a solid. Okay, so I have hydrochloric acid, which is HCl. Acids are always going to be aqueous. Reacts with magnesium metal, so Mg is off by itself, and that's a solid. So I write this charge up here just so I know it. I do not have to put +2 down here. Okay, so that's just up here so I know it whenever I bond it with somebody. Okay, so now I need to figure out what's going to happen. So basically is I have this metal right here is trying to take this hydrogen's place. So a positive can only take a positive's place. So this is single replacement. I'm going to write this over here. Okay, so this is where you refer to that activity series. I don't have it on here, but that sheet we give you that has the big arrow on the side, it basically ranks your metals. So the higher you are, the better you are. So chlorine is only going to dump hydrogen if magnesium is better. So you're going to look on that list. Is magnesium higher? It is. So that means magnesium is now going to go with chlorine. So magnesium has a charge of +2. Chlorine has a charge of -1, so they're not balanced. So you're going to do MgCl2. Okay. Plus, and now hydrogen's off by itself. So hydrogen got booted. So make sure you put this as an H2 because it is one of those diatomics. Okay, so MgCl2, if you're not really sure, just kind of go off your Cash and Gia. You can do that too. Or you can see that you actually started off with an aqueous in the beginning. So that means you're going to probably have an aqueous in the end. And there we go. So now what we got to do is we have to balance. I have 1 hydrogen on the left, 2 hydrogens on the right. So I'm going to go ahead and put a 2 right here to fix those hydrogens. That changes my chlorine. So now I have 2 chlorines. I have 2 chlorines on the right. I have 1 Mg on the left and 1 Mg on the right. So this one's balanced and done now. All I had to do is put that 2. Okay, so if it's single replacement, make sure you refer to that activity series. Number 2, potassium chlorate and sodium acetate. So potassium is K with a +1. Chlorate is ClO3 with a -1. Sodium is Na with a +1. And acetate is C2H3O2 with a -1. So I like these because if we have all the same numbers, this is going to be nice and easy to balance. So +1, -1, so they're already the same. So I'm just going to put KClO3. Okay, potassium's on my Cashingia and chlorate is. Okay, so this is going to be aqueous. And then sodium, Na, +1, so these are already balanced. So I just got to do is put these together. Okay, and then both of those are on my Cashingia list, so this would be aqueous as well. Kind of ran out of room there. Okay, so it looks like I have a pair and a pair. So this is going to be a partner swap. This is going to be a double replacement. So I'm going to take potassium and now mix it with acetate. So this is going to be a +1 and -1, so these are all balanced. So this would be KC2H3O2. Okay, both of those are on my Cashingia list, so this is aqueous. Okay, and then I have sodium +1, chlorate -1, so these are going to be balanced. So this is just NaClO3. And then both of those on my Cashingia list, so this is aqueous. So that's it. So that was a double replacement. With they're all being +1, -1, I didn't need any more of either one, so this is already balanced. So this is done. Iron 3 hydroxide. So iron, so Fe. So that means I have a charge of +3. Hydroxide, okay, is OH with a -1. So they're not balanced, so that means I gotta do my crisscross. So that means I need 1 iron, but I need 3 hydroxides. Make sure you put parentheses. That 3 cannot go on that hydrogen. It needs to go outside this. So remember my 3 rules for decomposition. So it tells you literally this is decomposition. So all I can do from here is break apart. Remember my first rule was if I can make H2O. My second rule was CO2. My third rule was O2. Okay, I can make H2O. Okay, because I have hydrogen and oxygens. H2O is a liquid. Okay, but here's the thing about decomposition you got to worry about is iron's not going to want to give up everything. It's like that clinging one that doesn't want everyone to go. Hydrogen's already left, and I've got some oxygens that are leaving. So iron can only hold on to that oxygen. Okay, so it's going to hold on to one of those oxygens. So iron has a charge of +3. Oxygen has a charge of -2. So this would be Fe2O3. Okay, so what I'm going to do here is iron and oxide. This is going to be actually make a solid. Okay, so your iron hydroxide. Neither of these are on my Cashingia, so this is going to be a solid as well. So this is actually done here. So all I got to do is balance. I have 1 iron on the left. I have 2 irons on the right. So I'm going to put a 2 in front of this. So now I have 2 irons. So now I got to see how many oxygens I have. So here I've actually got 2 times this, but there's 3 on that OH. So I actually have 6 oxygens on the left. And I only have 1 oxygen on the right and 4 oxygens on, 1 oxygen on the H2O and 3 oxygens on the iron oxide. So I've got 4. Okay, so I'm going to see if I can kind of come back to that one and see what we can do there. So I don't want to start doing things because you have oxygens in different places. So I'm going to see if I can go to hydrogen next. So I have 6 hydrogens on the left and only 2 on the right. Okay, so I'm going to put a 3 right here in front of this H2O to fix my hydrogens. Now I'm going to check my oxygens again. I still had 6 on the left, and now I'm going to check after I did that. 3 times 1 on this H2O is 3, and then I have 3 on the iron oxide, so now I have 6. So this one's actually done. Okay, so remember, usually try to keep oxygen for last because this is where you can kind of run into problems if you have oxygens in multiple places, like here and here. It just becomes a pain on where do you put a number. So that's why I usually save oxygens for last. Number 4, silver chloride and barium hydroxide. So silver is Ag with a +1. Chlorine is Cl with a -1. Barium is Ba with a +2. And hydroxide is OH with a -1. So AgCl, so this is already balanced. So this is just going to be AgCl. Okay, silver is a bad guy. It's attached to a halide, so this is going to be a solid. Plus barium hydroxide, barium Ba. hydroxide. So this is not balanced, so this is BaOH2. Neither are on my Cashingia, so this is going to be a solid. So it looks like this is going to be a double replacement because I got a pair and a pair. Okay, so I'm going to take silver and hydroxide, and I'm going to make silver hydroxide. So they're already balanced based on charge, so that's all I had to do. So this is going to be a solid. Now I'm going to take that barium and chlorine. So those are not balanced, so this is actually going to be a BaCl2. Okay, and now this is actually going to be aqueous. Okay, so now I'm going to look and see is everything balanced. One silver on the left, one silver on the right, good. One chlorine on the left, okay, and then two chlorines on the right, that's not good. So what I'm going to do is I'm going to put a 2 in front of this AgCl. So that fixes up my chlorines, but now it changed my silvers again. So now I have 2 silvers on the left and only 1 on the right, so I'm going to put a 2 right here. So now that fixes my silvers. I have 1 barium, and now I have 2 hydroxides and 2 hydroxides. So I am balanced now. Okay, solid magnesium oxide reacts with water. So Mg plus 2, oxygen is O with a minus 2. Reacts with water, that's just H2O. So this is going to be MgO, because they're already balanced, and this is a solid. Reacts with water, H2O, and this is a liquid. Okay, so this is where you kind of look, is I technically have 2 pairs, but double replacement wouldn't really do me any good here because all I would be doing is switching oxygens. So you'd just be in the exact same spot you started off in. So this is actually going to be a synthesis. Okay, so remember my rules for synthesis is, let me write these right here. If I can make hydroxide, I'll make hydroxide. Or if I could make a polyatomic, like carbonate or chlorate. Well, I can't make a polyatomic, but I can make hydroxide. So that means I'm now going to take magnesium and bond it with hydroxide. So hydroxide is OH with a minus 1 in case you need that. So this would be Mg with a plus 2. So that means I need 2 hydroxides to balance out. Okay, and this is going to be a solid since both those are on my Cashingia list. So I'm going to look and see if it's balanced. 1 Mg, 1 Mg, 2 O's, 2 O's, 2 H's, 2 H's. So this one is already balanced. So this is actually a synthesis. So kind of look out for that. Is if the double replacement wouldn't do me any good, that means it's a synthesis. Number 6, propane, C3H8, burns in the presence of oxygen. Okay, this is a dead giveaway. Anytime something burns or combusts or reacts with oxygen, this is going to be combustion. So all you're going to do is you have C3H8 plus O2 gives me CO2 plus H2O. Okay, I'm going to try to just look at this basically based off how I can see. So propane is a gas. So first let me put my states of matter. O2 is a gas, CO2 is a gas, and H2O is a liquid. Okay, so actually I'll just go ahead and do it this way. I'll do the CHO. I have 3 carbons on the left, 8 hydrogens on the left, 2 oxygens on the left, and then I have 1, 2, 3 on the right. So I'm going to put a 3 in front of this CO2. That changed this to 3. Change my oxygens now. 3 times 2 is 6 plus 1. This is now 7. So I'm going to move on to my hydrogens. I'm going to put a 4 in front of this to get to 8. But it changed my oxygens again. 3 times 2 is 6 plus 4 gives me 10. So that means I need 10 on the left, so I'm going to put a 5 right here. And that means now I'm done. So this is at 10. So this is it. Aluminum hydroxide and sulfuric acid. Okay, so aluminum is Al with a plus 3. Hydroxide is OH with a minus 1. Sulfuric acid. Okay, so I don't see hydro. So 1, I know I'm always dealing with hydrogen for an acid. If there's no hydro, that means I'm dealing with a polyatomic. And since it ends in ic, that means I'm dealing with sulfate. So this is SO4 with a minus 2. So I can tell these aren't balanced. So aluminum hydroxide is going to be Al OH3. Okay, and then sulfuric acid is going to be H2SO4. Okay, so just kind of, if you need to go back to those acid namings, kind of look at those again, please do that. Aluminum hydroxide, not on my Cashingius, this is solid. And then sulfuric acid, this is going to be aqueous. So I have a pair and a pair, so this is definitely going to be double replacement. Okay, but I'm taking an acid and a base. Remember we talked about this, when you take an acid and a base, you're going to make water. So hydrogen is now going with hydroxide, so this becomes H2O. Okay, then I'm going to make a salt. I'm going to take that aluminum and that sulfate and put them together. So aluminum has a charge of +3, sulfate has a charge of -2, so I'm going to crisscross. So it means I need 2 aluminums. Okay, and then I'm going to need 3 of those sulfates, so that's SO4 with a -2. So, I'm sorry, with a 2 down here. Whoop. SO4 with a -2, that means I need 3 of them, sorry. Let me fix that. Okay, H2O is a liquid. Okay, aluminum sulfate is going to be your salt. Okay, sulfate is on your Cashingia list, so this is going to be aqueous. So now all I have to really do is just make sure I balance. So I'm going to go ahead and try that HOH trick here and see if that works. I'm going to cross off this H2O and put an HOH. Okay, this trick, if it just makes things more complicated, like if you start running into dead ends and stuff like that, or it takes you further down a rabbit hole, then you can just go back to use H2O, but usually it works. So I'm going to start off with aluminums. I have 1 aluminum on the left, 2 on the right, so I'm going to put a 2 right here. So that affects my aluminum, so those are good, but it also affects my hydroxides. I have 6 on the left now, and I only have 1 hydroxide on the right, so I'm going to put a 6 in front of this. So that fixes my hydroxides. So I'm going to move on to hydrogens now. I have 6 hydrogens on the right and only 2 on the left, so I'm going to multiply this by 3. So that fixes my hydrogens, and now I have 3 sulfates and 3 sulfates, so now this is balanced. 8 iron and oxygen yield iron 3 oxide. So iron is Fe, and it told me iron 3 oxide, so this is +3. Doesn't matter right now, but and oxygen yield iron. So oxygen O -2, iron 3 oxide. So this is going to basically just gave me everything I needed. So iron is going to be a solid plus oxygen gas. So O2, and that's a gas, is going to make me iron 3 oxide. So those are not balanced, so make sure you crisscross. So this is Fe2O3. Okay, so this is going to be a solid. So now just make sure is everything balanced. Okay, irons are not balanced. I can go ahead and put a 2 right here to fix the irons. Oxygens, I have a 2 and a 3. Not going to go in each other, so 6 is going to be the closest number divided by both. So I'm going to put a 3 right here. And I'm going to put a 2 right here to fix my oxygens. But that changed my irons again, so now this is going to be a 4. Okay, so this one is actually done. So they actually kind of gave you everything there. So if you look, I have 2 parts making 1 whole, so this is going to be a synthesis. Number 9, calcium chlorate decomposes. So calcium is Ca with a +2. Chlorate is ClO3 with a -1. So I'm going to put these together, and I get Ca chlorate in parentheses with a 2. Okay, so this is going to be aqueous. Decomposes. So it just told me this was decomposition. So remember my rules. If I can make H2O, CO2, or O2, I'm going to make those. I can't make H2O. I can't make CO2. That is not carbon. That's chlorine. I can make O2 gas, though. Okay, so oxygen is going to go off on its own, do its own thing. So oxygen's trying to leave the building. Okay, remember calcium, remember decomposition, they don't want to get rid of everything. So now oxygen's leaving. So that means it's actually going to hold on to that chlorine. Okay, and chlorine is Cl with a -1. So that means I'm going to get calcium chloride, which is CaCl2. Okay. So, calcium chloride, this is going to be a solid, because I basically came from my gas. So this can actually kind of go both ways. So calcium chloride. So I'm going to put, I don't know why this is put, I don't know why the key says it's solid, but this could be aqueous as well. So I'm going to change this to aqueous. Again, states of matter are not going to be the main thing here. It's mostly they're going to be your formula. So now I got to see, is this actually balanced? It is not. I have 1 calcium on the right, on the left, 1 calcium on the right. So that one's good. I have 2 chlorines on the left. So remember this 2 kind of like cross multiplies. 2 chlorines on the left, 2 chlorines on the right. So those are good. I have 6 oxygens on the left, only 2 on the right. So I'm going to put a 3 right here. And then that means that one's done. Potassium metal, so K plus, and aqueous calcium hydroxide. So plus 2, OH minus. Okay, so I'm going to write small on this one, so K plus, which is, I'm sorry, I don't know why I did that charge. I don't need that in there. So K, which is a solid, plus aqueous calcium hydroxide, so this is CaOH2, that's aqueous. Okay, so it looks like I have potassium. It's trying to make its way in on the hydroxide. Okay, so I have to see, is potassium better than calcium on that activity series? So potassium is better than calcium. So hydroxide is going to dump calcium and go with potassium. So now you have potassium, which is KOH, with hydroxide, so plus 1, minus 1, so those are nice and balanced. And then now calcium's off by its lonesome. Okay, so calcium is going to be a metal, which is solid. And since I came from an aqueous solution, I'm going to keep this aqueous. So I'm going to see if it's balanced. So K is 1. I have 1 K on the right. I have 1 calcium on the left, 1 calcium on the right. I have 2 oxygens and 2 hydrogens on the left. So that means I'm going to multiply this by 2, which gives me 2 KOH. So that fixes my oxygens and my hydrogens, but that changed my K again. So that means I have to put a 2 right here, and this one's done. So I had a single taking another place and giving me a single. So this is single replacement. Okay, barium oxide, so Ba plus 2, oxygen with a minus 2, carbon dioxide gas, so this is going to be CO2 with, so I'm just going to leave it as CO2 right now. So if I were to write this out, so this would be BaO, that's a solid, plus CO2, which is a gas. I technically have 2 pairs, but again, all I'd be doing is switching oxygen, so that doesn't do me any good. So this is actually me a synthesis. So remember, if I could make hydroxide or a polyatomic, that's what I'm going to make. Okay, so I'm looking at what I have. I have CO2, so that means I could make carbonate. Okay, carbonate is CO3 with a minus 2. So that means barium is now going to go with carbonate, and I'm going to get BaCO3. Okay, and this is going to be a solid, and everything comes out balanced. So this one's actually done. So this is just kind of those rules you kind of got to look out for synthesis and decomposition. 12, calcium nitrate and potassium phosphate. So Ca plus 2, nitrate, NO3 with a minus 1, potassium K plus 1, phosphate PO4 with a minus 3. So these are not balanced, so this can be Ca, NO3, 2, which is aqueous. These are not balanced either, so that means I'm going to need 3 potassiums to balance out with that 1 phosphate. Okay, that's going to be aqueous as well. I have a pair and a pair, so this is going to be double replacement. So calcium's going to go with phosphate. Those are not balanced, so I'm going to crisscross. So I actually need 3 calciums and 2 phosphates. Okay, neither are on my Cash and Geo list, so this is going to be a solid. And now potassium's going with nitrate, so this will be KNO3. And this is going to be aqueous. Okay, so you can see here is I made a solid from 2 aqueuses. Okay, so there's one of your driving forces to make precipitate. Okay, so now I got to balance. 1 calcium on the left, 3 calciums on the right. So I'm going to go ahead and put a 3 in front of this. I actually have 6 nitrates. Okay, on the left. I'm sorry, 2 nitrates, sorry. I don't know why I was doing that. That's good that I actually did that, though. Is you're not multiplying this 2 times that 3 in there. So I only have 2 nitrates to begin with, but then I put a 3 in front of that. So now I have 6 nitrates. And I only have 6. I only have 1 on the right, so that means I'm going to put a 6 right here. So that fixes my nitrates. But now my potassiums are 6 on the right, and then I need 6 on the left. So I'm going to multiply this by 2. So now I have 6 potassiums on the left, 6 potassiums on the right, so we're good. 2 phosphates on the left and 2 phosphates on the right, so that means we're done. Solid calcium carbonate decomposes, so Ca with a +2, carbonate CO3 with a -2. So these are balanced, so this would be CaCO3. Okay, and that's a solid. So remember your rules for decomposition. Okay, if I can make H2O, CO2, or O2 in that order, I'll make those. I can't make H2O. I can make CO2 though. So that's my gas. Plus, remember, calcium is not going to want to get rid of everything. It's going to hold on to one of those oxygens because carbon already left. So this is going to be calcium oxide, CaO, which is going to be a solid. So this is decomposition, and this one's already balanced, so this one's actually done. Nickel 2 oxide, so Ni +2, oxygen with a -2. Silver is Ag with a +1. Okay, now that may not matter, but we're going to check. So this is going to be nickel oxide, so NiO. Okay, that neither on my cash and GS is a solid. Plus silver metal, which is by itself, and that's, oops. So that's going to be a solid. So I have silver trying to take nickel's place. So you have to look on your reactivity series, okay, and see, is silver better than nickel? It is not. So if silver is not better than nickel, oxygen is not going to leave nickel. So that means this is just going to be a no reaction. That's all you would write. So if the element is not better, okay, it's going to be a no reaction. 15, solid magnesium chlorate is heated. Okay, heated means we're going to break down, so this is going to be decomposition. Sorry, that last one is going to be it would be a single replacement. Okay. So magnesium, so Mg +2. Chlorate is ClO3 with a -1. So this would be Mg ClO3 2. And we already said this is a solid. Is heated. Okay, so that means we're going to decompose. Okay, so if I can make H2O, can't make it. I can't make CO2. I can make O2 though. That means magnesium is going to hold on to that chlorine. So this becomes MgCl2. Okay, so this is going to be a solid. So now I have to make sure I have balance. I have 1 Mg, I'm good. 2 chlorines, I'm good. Okay, I have 6 oxygens on the left. I only have 2 on the right, so I'm going to put a 3 right here to get that to 6. And that means this one is done. Iron 2 hydroxide, so Fe +2, OH with a -1. Okay, so FeOH2 is how it's going to look like once it's balanced. Okay, neither are on my cash and GS, so this is going to be solid. Okay, so if I can make H2O, I'm going to make H2O, so I can. Okay, iron is going to hold on to one of those oxygens since hydrogen left, so this becomes iron oxide, which is a solid. So this one actually comes out to be balanced, so this one's actually done, and this is decomposition. Okay, combustion, CH3OH, so CH3OH. Usually these are going to be gases, but not a big deal right now. Plus O2, which is a gas, and I'm going to always get CO2, which is a gas, plus H2O, which is a liquid. So this just becomes a balance. So I'm going to do my CHO. I have 1 carbon on the left, 1 carbon on the right. I have 4 hydrogens on the left, 2 on the right. I have 3 oxygens on the left, and then 3 oxygens on the right. So I'm going to move on to hydrogen since carbon's good. So I'm going to put a 2 in front of this H2O. That changes this to 4. Okay, but now my oxygen's 2 times, so 2 plus 2 gives me 4. So remember, the last thing I want to do is to touch anything here. So this 1 is not going anywhere, that 1 oxygen. So 1 plus what gives me 4? That would be 3. So that means I would have to multiply this one by 1.5, which is fine. I'm gonna put that down. If I get stuck here, what I'm going to do is I'm going to double this. This becomes 3. This little imaginary 1 right here becomes 2. This little imaginary 1 here becomes a 2. And this 2 becomes a 4. Okay, and that means I'm balanced and done. That's it. Okay, and this was combustion. Okay, few left. Aqueous copper 2 chloride and sodium metal. So aqueous copper 2 chloride, so Cu plus 2, chlorine with a -1, and sodium metal, Na with +1. So this becomes CuCl2, and we said this is aqueous, plus sodium metal, and that's going to be a solid by itself. So I have sodium, looks like it's trying to take copper's place, so this is going to be a single replacement. So to see, is sodium better than copper? So it is. So that means chlorine is going to dump copper. So this is going to make NaCl. So +1, -1, those are already balanced. Okay, so this is going to be aqueous. And now copper is by itself, so this is going to be Cu, and this is a solid. Okay, so now I just need to balance. 1 copper, good. 2 chlorines, only 1 chlorine on the right, so I'm going to put a 2 in front of this to fix the chlorines. And now I have 2 sodiums on the right. Now I need 2 on the left, so I'm going to put 2 right here. And this one's done. Sodium carbonate. Okay, so Na with a +1. CO3 with a -2. Hydrochloric acid. Hydro means no O, so that means we're dealing with hydrogen and only chlorine. Okay, so this is going to be Na2CO3 plus HCl. Okay, acid is going to be aqueous. Okay, and this is going to be aqueous as well. So it looks like this is going to be a double replacement because we got 2 pairs. So sodium's now going with chlorine, so this is going to give me NaCl, aqueous. Okay, and then hydrogen is going to go with carbonate, so this is going to be H2CO3. And that's actually an acid, so this is going to be aqueous as well. So now I got to make sure I balance 2 Nas on the left, 1 on the right. So I'm going to put a 2 in front of this to fix that. Now I have 2 Nas, 2 Cls, only 1 Cl on the left. So I'm going to put a 2 here. So now I have 2 hydrogens on the left, 2 hydrogens on the right, 2 chlorines on the left, 2 chlorines on the right, 1 carbonate on the left, and 1 carbonate on the right. So this one's actually done. 20, ammonium phosphate. So this is NH4. Plus, and phosphate is PO4 with a -3. I'm just getting these off that polyatomic list. Lithium is Li with a +1. Hydroxide is OH with a -1. So, this is actually going to need, I'm going to need 3 of these. Oops, I was saying 3. I need 3 of these ammoniums to balance out that 1 phosphate. Okay, ammonium's on my cash and geo list is aqueous. And lithium hydroxide, this is LiOH. Lithium's on my cash and geos is aqueous. So this looks like this is going to be a double replacement. Okay, so that means I'm going to take NH4 with hydroxide. So +1, -1. So this is going to be NH4OH. Okay, so this is going to be aqueous because of ammonium. Lithium's going to go now with phosphate. So +1 and -3, so not balanced. So that means I need 3 lithiums for my 1 phosphate. And this is aqueous as well. So this is done, so I just got to balance. I have 3 ammoniums on the left, only 1 on the right. So I'm going to put a 3 in front of this That changes my hydroxides to 3, so I need to change my hydroxides to 3 on the left. So I'm going to put a 3 in front of this. That fixes my hydroxides, and now my lithiums match, and now my phosphates match. Okay, so that's pretty much it. I'm going to do one more example just to cover another one of single replacements. Okay, so say I had something like, let's see. So say I had fluorine gas plus sodium chloride. Okay, so what happens is fluorine is now trying to take chlorine's place. Okay, so non-metals are not on that activity series. Okay, so you're just going to simply look on the periodic table and see if fluorine is higher than chlorine. So just like you would do on the arrow, if it's higher, it would happen. So if fluorine is trying to take chlorine's place, and fluorine is higher, that means sodium is now going to dump chlorine and take fluorine. And now chlorine is off by itself. Okay, so that's single replacement if it's a non-metal. So if you can't find them on that list, that means you're looking in the wrong place. You need to look on the periodic table. So fluorine, the higher you are, the better you are. So that means if I had something like iodine trying to take chlorine's place, okay, iodine's lower, so it's not any better. So this would be a no reaction. All right, so that pretty much covers single replacement and all the examples. So hopefully that kind of helped you out and stuff. So remember to make sure you practice your naming, stuff like that. Breaking always balanced based on charge. So that's why I wrote everything out individually. That's why it took so long. Okay, and then just make sure you have everything ready and let us know if you have any questions.